Okay, hello everyone. We're starting another stream for Linux Air Combat development. So this is part 4 of the series I'm doing where I'm refactoring this game, Linux Air Combat, to use modern C++, modern OpenGL, and just generally like cleaning up and modernizing the code base. So in the previous streams, what I've done is start building like a game engine and started working on porting the OpenGL code to run the to render all of the textures and models that we have that are provided as part of Linux Air Combat. So in the last stream in particular, I wrote the code that uploads and processes textures. So it loads it from the disk and then loads it into the GPU. And in this stream, I hope that I can start working on the 3D model loading code. So there's already 3D model loading provided with Linux Air Combat, which I think is actually a good starting point for how to handle this problem, because the file format that Linux Air Combat uses is 3ds models. So that's a proprietary format, and I don't know how to read it, and someone already figured out like all of the problems you need in order to read this file. So we're just going to port this code over instead of trying to write a new one from scratch. And once we have that, once we're able to load 3D models into into the CPU code, we can then send it to the GPU, and then we can render it with OpenGL. But okay, that means the first task we need to do is start actually porting over this 3D model loader from Linux Air Combat to our new C++ game engine. So let's see. I already basically copy pasted this code into the source code tree, but I need to actually like activate it because it's just not part of the build yet, because it's just going to cause a ton of errors. Oh, hello Braveskin, nice to see you again. So if we do activate this code, it's going to just cause a bunch of build errors immediately because I just took the code directly out of the old code base and put it into a new one, and basically none of these classes are defined. So step 1 would be porting all of these classes or coming up with some equivalent to them. So okay, so this is where all the errors start. So we have C model, which basically holds a collection of meshes and materials. And I've started a class in our game engine that will eventually hold the same data. So it's going to hold meshes and materials. So we can actually just start by including all of the code that we need here and seeing what the actual usage of the original code was. So yeah, this works with the old C model code from Linux Air Combat, and now we're just replacing all of these instances, or all these signatures, with our model code. This, of course, still will not compile, because we also need to actually rewrite the functions. But we can at least start by editing the signatures. Okay, so this is just a pattern that you see a lot in the Linux Air Combat code. A lot of memory is allocated on the stack using these fixed size buffers, and I need to figure out what the actual size for this value is. So we can go back into the Linux Air Combat code, where I originally took this. see, where's the 3DS loader here? And okay, it defines the buffer to be 256. I don't think that matters. I don't think the exact size matters, so this is fine. I'm going to change the error handling here because I don't want it to just terminate the program immediately. Hey, how's it going? Thanks for joining the stream. I'm not actually sure how to pronounce your name. It looks like Sakbiol Alam. Okay, we can also begin converting all these C vector 3 classes into GLM vec 3. There should at least be equivalent in the reason they're being used, but it won't have the equivalent API, which is fine. Okay, once we finish porting all the easy stuff, we can start working on translating all these API calls into a newer system. Okay, one thing I want to do is also take this binary file class, move that into its own source file, because there's basically no reason to be part of here, and it's kind of generally applicable. So we could possibly reuse this later on for something else. So we're just gonna copy paste this definition into its own file. I'm just gonna remove all this big endian code because I don't want to deal with that at all. Okay, actually, it looks like this buffer was only used to write debug strings, so we don't even need this anymore. And then otherwise, this file just reads a file onto disk, from disk into memory using the standard C file IO, which is pretty simple overall. The only thing that I kind of dislike about it is that it reads the entire file into memory, but that's a really minor problem, and I don't think it's actually going to be a problem for the data we have right now, because I expect these files to only be a couple of kilobytes in size, not multiple gigabytes. So as it is right now, this is fine. Okay, now we can actually start porting the model and object loading code from the LAC engine or from Linux Air Combat to our new engine. So that means that it appears that a model consists of multiple objects, and each object consists of a mesh and some like transform data. And wait, I can actually validate that by looking at the original object code. So that does not look right. That's not a C object. Hold on. There we go. Okay, so an object consists of some metadata, a material, a texture, a list of vertices, a list of triangles, or a list of quads. I assume that's mutually exclusive. And that appears to be it. Okay, yeah, the C model contains information like scale. And I'm trying to find where the information is that sets the position of a model. Like the world space position of a model, not of the position of the vertices. But maybe we can skip that right now and just do to porting C material. That should be the simplest one, since it basically just stores a bunch of data and that's it. So our material class right now contains absolutely nothing. And to start off, probably just going to do the exact same definitions that are included in the Linux Air Combat code. So pretty much all of this, except, well, we can use strings for the file names, but everything else is, we're just going to copy it. I know I have a color class from Linux Air Combat. Okay, I just need to include it or forward declare it. Oh wait, no, I need to include it. Then once we have all these fields defined, it should be pretty much already working for this. Yeah, so it's just writing material, U offset, and U scale. Okay, so that should work for just about anything that interacts with the material. Okay, so this is the function where it's just it's like the root function that loads all the materials in an object. So to do that, we need to actually retrieve the number of materials that are stored in the model. Okay, this has to be written somewhere. Okay, so it's the number of materials is controlled by add material, which I assume is somewhat called somewhere inside this. Oh, there we go. Okay, so it calls add material with a new texture, then process next material chunk. Okay, so that's one of the things we need to add to this model is a function that adds material. So at least for the initial versions, I want this to mostly match the way the API is used in Linux Air Combat. So we aren't going to drift too far away from that. Okay, so specifically this works by taking this material by pointer and then making a copy of it, which I don't think we need to do that explicitly when we can just use C++. Gabriel X C++, hey man, hey, how's it going? You joined one of these streams before? Okay, so the first function we're going to implement on this model class is add material. By the way, I want to change the casing that I used on this. That is one thing that I'm going to change, so it should be a pretty simple change without changing the behavior. And then once we have that, we just need to add to this vector of materials. Specifically, we're going to copy the parameter and store the copy in the shared pointer. Although I'm not sure we need to copy it again. Okay, what this function does, it has this material here called new texture, which is not initialized or anything whenever it gets passed in here. I'm not sure why they even bother copying this at all. It could just be a blank material, I guess. Yeah, as far as I can tell, there's only one. This is the only place in the code base where they call add material, and it's just called with this blank default value here. So we actually don't need a parameter here at all. Although what we can do is return the reference to the newly created material. Okay, so that means we just need to add a new entry to this list. And this constructor has 0 parameters, so it is just going to be basically a blank class. Yeah, this class is basically just a plain old data structure. And then we just return the newest element in the vector. So we just delete this, update the name. Oh, shoot. Update the name of the function, and there we go. So once we have the new material added to the model, we need to actually manipulate it by setting all these values. Okay, so here right away I see a pattern that they followed, they use quite a lot here, which is every single time they want to reference the last material, they get a new reference to it by calculating the last index, subtracting 1, and then reading from the array, which is very pointlessly verbose. So we can just port this over to our new system. Take a reference to this array element instead of just calculating it again every single time. No, I need to expose the material vector from the model. Specifically, I need a way to fetch individual materials by index from this vector. I think I need two versions for const and non-const. Yeah, and I need a way to get the actual size of this vector. Okay, now that we have this reference, we can replace every instance of this with the reference. Just within this function, so I don't want to update everything. Okay, I'm not sure what this get function call is from the original one. Oh, okay, so that's something I added earlier. It just gets the pointer from the unique pointer. Because this takes a regular pointer. Okay, so we can delete that. Now, all of these function calls expect a pointer. There's not really any reason for them to have a pointer, so we can change these to references, and we probably should, but it should have no like semantic effect on how this loads files. It will require rewriting a lot of code though, because instead of pointer dereferences, now you're doing reference. Instead of like the arrow notation for pointers, now using the dot notation for references. But these should be fairly small functions to begin with. Okay, so I think that ports over every single material loading function. Yeah, there we have 1, 2, 3, 4, 5 functions, all of which have been ported over to use this new reference. And I believe their behavior has also, or the function body has also been changed. We have 1, 2, 3, 4, 5. Kind of annoying that these aren't they aren't grouped together like they are in the header function, or the header file. No, yeah, see, that's one that I failed to update, so now I can do that. All right, what else do we need to make this load models? Okay, so a lot of code here manipulates the C object, which again, we go back to the model file. The model, the H in Linux Air Combat, the C model, or no, the C object contains a material, a vertex list, and a triangle list. Oh, you know what this triangle list is probably indices. No, I don't know what that is. Okay, that's a really weird way to set up your mesh data, and we're going to have to completely rewrite that. Okay, hold on. One thing I want to check is, does anything use the name or file name of this material setting? Visual Studio is not very helpful here. No, it appears that this data is never actually sent. But it is being read? Wait. Okay. I just was using the tools incorrectly there. Okay, yeah, this is being read. I need to change this to use dot notation. But this doesn't appear to actually be set anywhere. Oh wait, this is the function that sets it, because read string, it stores it inside this pointer. Okay. That means that, among other things, we need to add a function here to read from C++ strings instead of just C strings. Okay, so the existing function reads strings from the file byte by byte, and it looks for a null terminator to know when to stop reading. So I guess this file function has null terminated strings, which is really weird. But the easiest way to do this would be to just have a buffer inside here, which holds the temporary string as we read it from the file. And I did in fact need that int that I deleted earlier. Okay, so this is basically the same logic as the original function, but now it stores this string inside this stack allocated buffer, and then we can just copy that into the string. Okay, I'm not sure what that error means, but I'm just going to ignore it for now. Okay, we don't need to actually copy the null terminator into this buffer. Okay, that should be that should accept a C++ string into this parameter and then modify it. I'm not sure why these two source files don't actually recognize that function call. Oh, this is a different overload. Okay. Okay, so this is just the size, the maximum size of the string, and I'm not sure what this parameter means. So it's calling this overload. So n is just what? Okay, we're just going to copy this logic for what n is. And we need to add these parameters to the new function as well. Don't have a pointer max size, so that's not relevant. Okay, so this is actually defining a string of a known length being read from the file, so we don't need to go through this while loop then. Oh, whoops, I'm modifying the wrong file. Or the wrong function. So n is already known here. We don't need to copy it to a temp buffer. We do need to increment file pointer by n. There we go. That should be reading a string of known length from the binary file. And we can delete this size because we don't need that. Okay. This case statement here just changes the file name to be all lowercase, which I don't even know if that's really useful. Depends on if anything else ever uses this file name variable. Yeah, it might, so I'm just going to preserve that code as well. There should be a way to actually modify a C++ string with like a standard function here. Okay, so there's no standard function, you just have to write it yourself. Well, whatever. Okay, then we need to just update this function, read color chunk, to use material by reference. Okay, interesting. The color it's using is a binary color, or it's just a struct. But they're using the read string function on it. Okay, yeah, C is just the internal array here. Okay, so it's just a 4-byte array, and they're using the string function to read 4 bytes from the binary file. So kind of weird they're using a string processing function. We can in fact just add a new function here that reads a binary chunk or a binary blob based on a known size. Also, since we don't have an array called C, we just need to use a different one. We called it elements, which is an array of int4 or of uint8. Yeah, we cast it to a character pointer. Let's use a different cast there. Okay, I'm not sure what the correct cast would be. I guess we have to use a reinterpret cast. Okay, hold on. I just realized we can't pass n here because we don't actually know the length of the string yet. And I was wrong about how that function was operating earlier. Yeah, I'm pretty sure we just need to read it like a null terminated string array. What? I don't need to copy character by character and just use mem copy here. Okay, so that should convert all of the functions that use material to use our new material class. So back to converting a C object. Again, we have this vertex list, triangle list, quad list. I think this is equivalent to the meshes that we stored in our new model. So that'd be equivalent of a mesh class. Oh, okay. C model at the top level does define the vector3 position and the rotation. I'm not sure what this is called, TL null. Okay, that's really weird, but that's just a way to store like a 0 value that it uses for these GL translate calls. That's really weird that they have this 0 value stored in the middle of every single C model, but whatever. Okay, but that does allow you to define a translation vector outside of this, what's stored in the model. So that means whoever calls this can provide their own translation vector. Yeah, so the vectors are not, so like the translation and rotation matrices are not actually stored in part inside the model, which is fine. It just means that we need a way to define how to pass that data in through GL uniforms, which we'll be using later. Okay, let's start by looking at what we need to add and implement here. Okay, so just like how we defined get material count and get material, we need to do that for the meshes as part of this model class as well. Okay, so it seems like every model also has a reference to the material it uses, which I guess we can implement that later. Okay, so this function is actually making calls to GL by calling gen texture TGA. That means that somewhere it's loading a texture object in or texture object into the object class, and I suppose it does that by name. Yeah, this is where it loads the texture from the file name, and then it stores it in the texture class. This is a pointer that points to the texture that's used with this material. Okay, so that's why it has a reference to the material that's used for it. Where is this called? Okay, so it's called after everything is loaded in here. Why are you doing everything from the ground up? You already had so much done in Unity. This is a different project than anything I was doing in Unity, so this is just a project to port some C++ code from an old game engine into a new one. Doesn't replace or really undo any of the work I've done with Unity. And anyways, like digging into the low level of a game engine is always pretty interesting, even if it's not related to like probably don't plan on writing my own game engine, but this is still a good way to get experience with how game engines work. Okay, so something I want to do is like back in this load textures function. First, we need to find a way to, we need to store whether or not the mesh has textures, and we need to store the material that's in it. And then we need to, this is the, I guess, the single point where the textures get loaded. That means that since load textures is called after process next chunk, that means we need a way to store every material that's used alongside with the mesh. So I think that would be inside this file, it's going to store, or inside this function, it's going to store the mesh that's used, the material that's used with the specific mesh. Yeah, so let's start by changing over this function to our new code. That's read object material. Okay, so this is where it compares the material name that's stored inside the material with the material name that's inside this file, this like data chunk within the file. Material name is just a stack allocated array they call get string in order to read its contents. Okay. Okay, that Visual Studio took me to the wrong file for some reason. Okay, that should work now. Are you using light mode in Visual Studio to code for Linux? I am using light mode, and I think light mode is usually better than dark mode. And what I'm coding is a game that was originally written for Linux, and now I'm porting it to Windows. So it's called Linux Air Combat, and I'm getting it to run on Windows. I'm also rewriting the engine at the same time. Yeah, this is part of a larger series I've been doing. This is stream number 4. So I have the other streams where I worked on like porting the basic functionality of the game into like a new game engine. And right now I'm working on the model loading code. So this is the code that loads a 3D model from the disk into the CPU RAM, and then eventually loads that to the GPU RAM to display with OpenGL. So I'm basically porting over the functionality from the original code into this new game engine that I'm writing for this porting project. Okay, so the mesh does not currently store the material. I need to actually set that here. Okay, so we're just going to add a getter and a setter function here so we can store the material, which is a shared pointer, inside the mesh. Okay, so that means back in the model loader code, we need to actually store this material. And it's doing this string operation here, which I'm not sure what this does. Okay, it's checking the file name of the material, which I'm not sure is ever set. Oh, it's checking whether or not it has a texture, or it's setting whether it has a texture based on whether the file name is actually set to a valid file. That's a really weird way to handle that, but I can port that behavior over. Okay, so really the only check that I want to preserve is whether or not the file name is larger, the size of the file name is larger than 0. I also need to add a field to store whether or not there's a texture. Okay, so that stores whether or not the mesh has a texture. The other problem I need to solve is whether this field for material.file name is ever set. hold on. Read object material from the original source file. Yeah, it just checks whether the material has a file name, then uses that to set has texture to true. Then has texture is used later on. Compute colors, okay. And also load textures. Okay, so it checks has texture, then it loads it. It loads the texture based on the material file name. So that means that it's actually very significant what gets stored inside of this C material file name field. Oh, okay, so gen texture can return null. And if this field is set to null, then has texture is just set to false. So that's a weird way to load this. It's looking for a texture that matches the same name as the material. But other than that, that's like the only logic for defining textures. Okay. So I imagine on a lot of the plane models, this will actually be null, and nothing will really happen on this function. Okay, so the only two functions we need to port are this get textures function and the gl texture loading function, which I already have a way to load this. Okay, the texture is just a shared pointer that's directly exposed in this class. So we can just, yeah, assign it and check if it's null. Okay. So that was what I worked on last week, to load a texture based on file name. Yeah, texture load from TGA. Okay, so what is the alpha type? What is going to be set to this alpha type argument? That depends on what gen texture TGA is asking for. So let's see. Alpha type here is set to -1, which means that it's a special value that means nothing. So texture alpha type none, which is set to -1. Okay. Okay, so now this load from TGA expects there to be an existing texture at the file name, so we need to add another overload or another function here that will return whether or not a texture actually exists. So instead of load from TGA, we're going to do try load from TGA. Actually, we don't need both of these functions. We could just make this well, okay, let's just keep both functions for now. No, okay, let's yeah, let's just have the only function be try load from TGA. Now to actually check whether it loads function properly, we're gonna, if this data variable is null, then we just return null, and that's considered a failure to load. Okay, so that returns us a shared pointer, which we can then check for whether or not it's null. Now the only thing we need to port is this dir's get texture function, which was basically this class from the Linux Air Combat original code, which we may as well just copy and paste directly into our new game engine. Yeah, the dirs variable is this static unique pointer, which I don't think is a very good way to handle this. In fact, this entire thing can basically be reduced to a static class with a bunch of static calls. There's no need to create an instance of the directories class, which is what dirs stands for. We also need to copy platform folders, which is a single header library. Okay, I don't remember the syntax for that. Okay, there we go. I hope this works as a static initializer variable. Okay, so that should properly load textures from the 3ds model format and store it into our new game engine model object. I, of course, can't unit test this because there's still all these other errors that I need to fix and port over this new functionality. But I am going to save my progress right now by committing this to Git. Okay, so for the model class, we're now adding the ability to add a mesh to the model class, which is basically just instantiating this the shared pointer, and then returning that, and that will allow us to create the object in the model without having this temporary object on the stack. We don't need this or this. Okay, and this wants to read the mesh from the name of the wants to read the name of the mesh from the file. So we need a way to store this. Okay, so I basically wrote a move constructor and a copy constructor, although it's just a function call instead of an actual constructor here. Not really relevant to the game engine, but it's just good C++ practice to include options like that. So you can either copy or move the string as needed. Okay, so that allows us to read the name of the string and then store it in the mesh. Okay, so apparently we need a way to store the scale of a model, which is just a single float variable. Okay, hold on. I think this call is unnecessary. We just pass the material reference into this next call. But this is recursive, and I don't know if this is actually going to modify the material whatsoever, so. I believe the only call to add material is inside process next chunk. And this is only called once. So I think this should be safe. Okay, so this function, now we're going to start loading the mesh data into our mesh class. So this function reads the UV coordinates and stores it inside the mesh. So the way it does that is it reads the number of vertices, then it creates an array that stores that, which is just a temporary array, then it copies that into the mesh object and then deletes the array. I think there's a way to simplify this without actually needing to create this temporary array. But first I need to figure out what is this value here. Oh wait, this is reading the uint16 and then storing it inside the num text vertex. Okay. So we don't actually need that as it is right now. And here we can start using this vertex data class that we created a while ago. So what we are storing are UV coordinates. We need to select this mesh data enum to be UV. And it's probably going to be a float32 vec2. Yeah, it's a C vector2 object, so that should be float32 vec2. Which will be stored inside this vertex. We need to create a vertex data class with these parameters and then use that to create our mesh data. Hold on, how do you actually... Oh, okay. Okay, the only function I wrote for it just allows you to copy from a buffer of a known size. You're copying from this file buffer. I don't want to copy it to a temp buffer, so there needs to be a different way to actually do this. Okay, so since the local data is just a vector of character, it's very easy to just resize this vector. So it's basically the same class, or the same function here, but just we aren't copying any data from this data pointer. So since we know the number of vertices that we're loading, we can start creating our vertex data class. Which is going to have the mesh data type of UV. a vertex format of float32 vec2. I just realized I could probably split this into two separate parameters instead of just how this is combined in a single parameter, but I'm not going to do that for right now. Then for our vertex data, we can call the resize function. And we need to get the total size of the buffer, not just the number of vertices we have. So it's going to be, well, since we know it's going to be exactly float32 vec2, we can just take the size of the GLM type, which is going to be GLM vec2. Okay, so this function takes the number of floating point elements and just reads them as a big array, okay? No, I did not write the read binary function. Oh. We don't actually need to handle them as individual floating point elements, so we can just copy the entire array as a binary blob here. We should make that type int. Yeah, that matches the signature we defined here. So now we can just load this directly into the buffer we created inside the vertex data class. Hold on, we need to copy this as well. Oh, this is a const function. Shoot. Okay, we also need a non-const version so we can write to it directly. Okay, and that allows us to delete all of this code where we create a temporary array. And now we just need to repeat this for the other mesh data that we are going to need. We're going to skip this for now because that's vertex indices, which is a little bit harder to load. But the vertices should just be the position vertices. So it's going to be the position, perhaps the vertex color of that vertex. Okay, so once again, we're going to create this stack variable to store the number of vertices. Okay, I see what this is doing. Okay, this function creates the array. It allocates the array to store inside the mesh object and sets it to 0. And it creates the temporary array, which it reads directly from the file. And then it flips around the vertices to account for 3ds Max's different coordinate system. And then it just deletes the temporary. So this is basically changing the coordinate system into whatever Linux Air Combat uses, which is a fairly simple operation. So we can just copy this logic again. And that means we do need another vertex data object. Instead of UV, now we are using a different type. It's going to be position. Float32 vec3. We're just going to get rid of this allocation code here. Okay, I do need to check what the type of C vertex is. Yeah, C vertex contains a color, vector, normal, and texture. And the only thing this is doing is updating the vector of the vertex object. So I need to figure out how this is called. Okay, yeah, so the first vertex call actually creates the vertex with all of the subfields. And then the read UV later on just populates this with its own data. We don't really need to copy that exact behavior. Oh, I just realized we do need to add this to the mesh object. So add vertex data. there. Okay, so the API I actually wrote for this has a shared pointer of vertex data. Okay, so on UV coordinates, we create the vertex data, we populate it from the file, and then we add it to the mesh. For read vertices, this is going to be the vertex position data. We're going to do the same thing, so we need to create the vertex data as a shared pointer. Then we need to read it from the file, then store it to the mesh. Okay, so we can get rid of all these temporary memory allocations. Why is that not valid? Oh, again, we just need the binary file and the total size that we're allocating. Okay, now to read the vertex indices, instead of individual vertices and the vertex data, which is like vector 3, we're just reading 16-bit integers, which will define like the index triangle list, which we submit to OpenGL later on. Okay, but again, I don't understand what this triangle object is supposed to be doing here. So it's a array of length 3 to a pointer of vertex objects. Yeah, and then it just reads these individual vertices from the existing vertex array. Notably, it doesn't actually use this index for anything. It's a really weird way to handle this. I know there's another function near the top of the file which merges vertices, which is like completely pointless because they're already shared whenever you read from the index buffer. So I might just eliminate this compile function, or at least this part of the compile function. That means for our meshes, we need to add another data field, which allows us to store the index of the triangle list, which is not going to be the same as vertex data. It's basically just a vector of uint 16. And whether or not a mesh actually has vertex data, I guess that's optional. So we need to have a way to specify whether or not, or whether it has index data is optional. So we need to specify whether it actually has index data defined, or just an array of length 0 for index data. Okay, so this API is going to have the ability to check whether index data is actually enabled. Oh, there also has to be a way to set whether index data is enabled. get the size of the index data, and then get the index data itself. I guess this should just be a raw pointer. We don't need to expose that it's a vector. Okay, so has index data, get index data count, and get index data, and then the functions to mutate it. So this will allow us to actually write to the index data from the model loader. But first, we need to implement these functions. So this is mostly the same as the Vertex data API. We're just rewriting it in a slightly different place. But yeah, we need to resize the M index data, and then we need to mem copy the relevant data. And then this set of functions will just allow us to write directly to the data. Which is what we're actually going to be using in the model loader. Okay, so now that we have the read uint16 function here, this gets us the number of indices we need to load. So object set index data. Wait, what? Yeah, resize index data based on the index count. And then we can read from the file another binary blob to object.get index data. Index count times size of uint16. That will copy over everything that we need. Now we need to cast this. And now we have a list of, now we have a vector that has our index data in it, which eventually we will pass to OpenGL in order to render our mesh. Then finally, we need to enable the index data. So I'm basically going to skip over everything they're doing here, where they're just copying pointers to vertices, which is a really weird and inefficient way to handle this. And now we have our index data being read from the the file. Okay, I don't actually see a way to load vertex colors from here, so I don't think it ever happens. I don't think these meshes have any vertex colors. And then I don't understand how they actually get colored because most of them don't have textures either. Oh yeah, we needed to fix up the vertices for the coordinates. Yeah, we're just reading it as a binary file. We need to actually read it as floats. Okay, so we're just going to read directly from the local data pointer, reinterpret it as a vector3, and then read this as a GLM vector3 object. And then the actual logic they have to do this is they swap the y and z, then they negate z. Okay, so y becomes the old z, and z becomes negative old y. Now the temp y stores the y. Okay, so that should flip the coordinate system. The only thing I don't see is how or if they modify the vertex colors. Okay, so that's what this file does. It loads the colors based on either the material color or the texture. Hold on, it looks like this is doing a CPU side vertex color texturing, which is a very strange way to handle this. And I don't think these even use textured models that much. So, okay, we need to actually modify this as well. So it looks like every mesh that's loaded through here it will have vertex colors. If it has a texture, and we actually sample the texture, and we write it into this color object, or into the vertex color, with this weird logic to transform the actual color. I have no idea what this is supposed to be doing, but I guess we have to translate that. Okay, I don't want to do CPU side sampling for these textures. There's basically no reason to actually do that, especially in modern OpenGL. So, just eliminate this completely. And then just invert the case, and now we have to set the vertex colors based on the material color. Okay, so once we're in here, we know for sure that we need to create the vertex color data. Okay, so that's going to be enough data to store the vertex color, or that's the right format to store vertex color. Now, we may need to add some helper functions to these vertex data. I don't know the way to get the actual vertex size. And this would just be a simple case statement. Okay, now that we have this function to calculate the vertex size, we need to actually calculate the vertex count based on what's loaded into local data. Okay, so the number of vertices that we have is not going to be known until we actually find the correct vertex data. That means that once we're here, we need to search for the vertex data, or well, these should all have the same number of vertices in each vertex data object. So we can just take the first one on the list and use that as the vertex data. Oh, we need to expose the vertex count. Okay, so m count is set by resize local data, which is the binary size of the local data divided by the vertex size. Actually, let's do this. So we get the binary size. All right, there we go. Okay, so calculate the vertex size. We make sure that the actual size of the data is a multiple of the vertex size. And for here, we can just calculate this again. So size is going to be m count times size. Okay, so we have the object. We can get vertex data. We can get the first vertex data. And then get the vertex count from that. Okay, kind of blowing up the total number of methods here, but no, I don't want to add that. Okay. This is the count of vertices. We need to store this size data. Okay, and now that we have this local data sized correctly, we can take a pointer to it. I think there's yeah, I8vec4. So that's the GLM type that matches this Vertex format. Okay, so we have this array of colors. Actually, we should store the object material in a temporary variable. Okay, now we can write the for loop that actually sets the colors of this vertex data. Okay. I actually defined the colors to be an array of uint4, or uint8, array length 4. But that should be identical to what I already have right now. Okay, so that should load the vertex colors properly. We need to compute the normals of each triangle. I don't think that's the right way to handle this. That should be a per vertex normal. No, I'm going to skip that for right now. I have no idea what this function does. But once we translate those functions, we should actually be able to load a model. Okay, I really want to delete this because I don't think it's even necessary. Okay, scale texture coordinate by U scale and V scale. What the heck does that do? Yeah, this is called immediately after processing. And before it actually computes color. Okay, I don't think that's necessary either. Yeah, that can be handled in a shader, so this entire function can be eliminated. Okay, so there's only a handful of things we need to compute now. It looks like it's clamping the values that come out of the mesh. I don't think that's necessary either. Oh, this is like normalizing the vertex positions based on the maximum size of the vertex. Again, I don't think this is necessary. Yeah, that wasn't clamping it. That was finding the minimum and maximum size for each vertex. Okay, so the last step we need to translate is compute normals. Okay, so I guess the 3DS models don't have normals in them. Wait, what is a mesh matrix? Okay, we're just reading the data and they do absolutely nothing with it. Okay, so I'm not sure what we're supposed to be doing with these normals. Because it looks like it's setting the normal value for each vertex. But where's this normal actually populated originally? So yeah, we have vector 3 normal. Wait, what? Okay, this is like averaging the normals from each triangle. Okay, I think it's like computing smooth normals based off of whatever's available. Okay, I think I just want to put like flat shaded normals into the mesh for right now. Doing that will require me to put a normal vertex for every position vertex based on the triangles that are inside the index list. Okay, so this is the number of vertices that we need. And we're going to store our normals in a GLM vec3 format. And we need to have different behavior based on whether or not there's indexing or just direct vertex reads. Okay, so to actually compute a normal, we need to get the 3 vertices that form a triangle, get the cross product from them, and then use that to build the normals. But we need to actually identify the 3 vertices. Okay, so this function is going to take 3 vertices of any kind and use that to compute the normal. No, I don't want to define it here. Okay, I don't remember the rules for the winding order. Although the normal should be exactly the same no matter which ones you choose. So we're going to choose v1 as the center of the cross product. And then we're going to build vectors that go from v1 to the other ones. Okay, so we take the difference between these vectors, normalize them, and take the cross product, and that's the normal for this triangle. Okay, what was the other thing I modified earlier? Okay, I need this as well. Well, I need to find the vertex data that has the vertex positions as well. Okay, so once we have the position data, vertex data stream, we can fetch a pointer that represents, lets us read into the data. We need this for both the position and the normal data in order to calculate the normals. Okay, I need to improve this API because putting this into a const reference is kind of awkward. Anyways. Okay, so if it doesn't have index data, then doing this operation is very simple. We just calculate it for every 3 positions, and then we set that to the we set the normals to the normal value of compute normal. Okay, so we need to process these vertices 3 at a time, which means we need to skip by 3 vertices every time. And we need to make sure that we don't read past the end of the array. Once we do that, we can just read 3 vertices from the position array and use that to compute the normal. By the way, I should call these P1 instead of V1. Okay, so now we can extract each vertex from the position array. And then we can compute the normal. And now we write the normals back into the normal array. Okay, so that was the easy case whenever we have no index data. For index data, this is going to be a lot more complicated because we need to fetch the indices and then fetch the positions. Well, okay, that's not a lot more complicated, but it's still more complicated. Okay, so that gets us the index data. And we also need the index data count. Well, okay, let's store that outside. Okay, same basic logic here. We need to make sure we don't go past the end of the array. And we need to get the index from the array first. So we're going to get I1, I2, and I3 from this index data array. And then we can pretty much just copy paste this, but use the different indexes. Okay, that should load or compute the normals now, and that was the last thing we needed to finish writing the model loader. So I haven't tested this yet, but I'm still gonna commit the changes I made, just because they were so large. Okay, this should fail to build because I know I broke some stuff elsewhere. Yeah. Okay, I don't know why that broke. That should not be breaking. What? Okay, yeah, I was expecting this to fail. Okay, I don't understand why this operator is failing now. Oh, because this is a member function. I need to make this like a static function instead. Well, I need to make it like a free function. Okay, I'm getting shared pointer errors, but those don't show me the actual line that's failing, which is a very annoying part of Visual Studio. This is basically a stack trace, but a compile time stack trace. And it's enormous. I have no idea what this is supposed to be pointing to. Okay, it's inside the model.cpp function. Something in here is creating a shared pointer incorrectly. Let's see, we have a vector of shared pointer, and that's probably what's causing the problem. Oh, that's the problem. I need to change that type. Okay, when you have some more linker errors here. I think this needs to be an inline function. There we go. Okay, so the TGA loader works fine. It's not really the most important thing I was looking at. I need to write a new test file instead of just writing model loader or model viewer directly. Hold on. Model loader, TGA loader. There's a new. I need to make a new folder here. Okay, there's some other stuff here I could delete because I don't need really any of that. I just realized I don't know how to actually get a model out of this. I think you just pass a model reference and it modifies it in place with a specific file name. Okay, so instead of that, I need model. Okay, I need to include this file and also, well, I just need to include the file. Oh, I called it Mesh Loader 3DS. Yeah, change that name. Okay, the model I'm trying to load here is located in the folder data a6m2.3ds. Also, I need to modify the CMake file. Where's it getting that name from? Anyways. I don't think I put that name anywhere else. I'm not sure where it's getting that name. Okay, some more include errors I need to fix. All right, we got some linker errors. Okay, inside compute colors. It says that one of these functions does not exist. I really wish this linker actually gave information on what the heck is failing. Yeah, the constructor. Oh, I just never defined it. All right, now there's a different linker error. Inside directories maps. Okay, so I just need to find this as well. All right, so that solved all the linker errors. Now we can actually test whether the 3D model loader works. Well, according to this, it does work. It ran without issue, but I don't know if it actually loaded the data. So I don't really want to stop right now, but we can start working on the actual model viewer now. Well, okay, not the model viewer, but we can write the actual rendering code here. And this should actually work just fine as the model viewer. Okay, we don't have the 3D perspective yet, but we have everything except for that. Okay, so this does already load multiple vertex streams. So once we, no, I didn't want to close all these files. Okay, so we should be able to load the model right here. And then use that to render something. A6M2.3ds. Okay, there we go. We're starting to hit errors, which isn't a good thing, but at least it means that we are in fact running the code. Okay, so it's not even loading a mesh right now. It loaded one material and nothing else. Okay, that's kind of weird. Okay, so it's not even loading a mesh right now. Okay, so somehow when loading the material, it's not processing the file correctly. I have a feeling it might be related to these name strings, which I'm possibly not reading correctly. So before it was using this 3-parameter name or read string function. Okay, I think I see what the problem is. Let's see. Okay, so read string, this just reads until the next null terminating or null character, which is not it's not correct. Okay. So I need to add a new overload here that takes this n parameter, int n. I use that to read a string of size n. Okay, now I need to go back to the original way this was written in Linux Air Combat. Okay, yeah, the n they're submitting to this function is the size of the current chunk. Basically, it's telling it to read to the end of the current chunk. That might be why it was reading data incorrectly. How many places do I call this function? Okay, I think that might be every place where I use the new string-based overload. Okay, but anyways, back to the loading program. Still loading nothing for the meshes. And this string is still invalid. Okay, I want to use the old 3ds loader code to compare how it looks whenever you load it through the data format that we know is valid, or through the loader code that we know is valid. Isn't there should be j plus equals 3? What are you talking about? Possibly watching an earlier version of this, or an earlier location on the stream, so. Okay. I think it means j plus equals 3 right there. And yes, that would be correct. But the problem is we weren't even hitting this code to begin with, so that doesn't solve the current problem I have. Okay, like I said, I want to use this old model loader code and use this to compare what this should look like when it's loaded properly. I think it'd be very difficult to put this into my new model viewer executable though. I may just have to inspect how it looks like in the game. So line 11,000 of the main function, or of the main file, that's where it actually loads the A6M2 plane. So we should be able to see something in this mesh. Let's see, num object is 12 and num materials is 9. Yeah, so the code I wrote was only reading one object and zero. It was reading one material and 0 objects, so I'm definitely doing something very wrong there. Okay, so process next chunk. Let's just start putting break points everywhere here. and go back to model viewer and see how many breakpoints we actually hit. Okay, so we get the version correctly. We go to this one material and load it. Let's see, the size of the file pointer, or the size of the file is 146 kilobytes. And we're 20 bytes into it. And then it exits. So this entire while loop did I change the way this flows? Process next material chunk. Wait, that's not even the right one. Process next chunk. Yeah, so the original model loader here, process next chunk. Previous chunk bytes read is less than previous chunk length. Current chunk. So something in here is where we're exiting the function. Now we go here and we go to file, file pointer. We've read the entire function here, or we've read the entire file, and that exits. So something inside this material call is causing us to read the entire file. Okay, so we have the material chunk, the material name. See, we have not read the material name yet, and we are currently 34 bytes into the chunk. Okay, now we're 53 bytes into the chunk. Material name is set to none A6M0. I'm not sure if that's correct. Okay, we're 53 bytes into it. We read the diffuse color. That brings it to 78 bytes. All right. And then we exit entirely. So none of these other breakpoints were hit, and that read the entire file. So was it inside this read diffuse chunk? I'm pretty sure mat name is reading correctly. File is 68 bytes. Okay, that's a different number than I got earlier. Oh, there we go. We read 78 bytes. And temp chunk read 10 bytes. Okay, so for some reason the current chunk length is set to this very high value, and that's causing us to skip the entire file. Okay, we are switching on current chunk ID 4000. Okay, let's go through here again. We have not yet read the name, so the current chunk ID is unknown. And that causes us to skip a couple of chunks. Back to current chunk over here. Then we mat diffuse. Current chunk ID is 40,992. Okay. We read the color chunk, and now we go here. We read current chunk is 4,000. So somehow we're reading this incorrectly and causing it to become misaligned with the data. Something inside read color chunk. Okay, so I did modify this to use read binary instead of read string. It's possible it was using a different read string overload that's not correct anymore. Yeah, whatever this logic is doing might have an effect on read binary. Okay, so the current chunk is the mat diffuse chunk. And then we create a temp chunk out of that with a length of 9 and a bytes read of 6. Oh, okay, so that's the reason why it's failing. There's a length of 9 and bytes read of 6, so that gives us 3 more bytes to read. Instead, I've been reading 4. So that's been just misaligning the entire data. No, that's still bad, actually. Okay, length is 15 and bytes read is 6. When we exit that function, bytes read is 16. So we're still reading the data incorrectly here. Okay, I see. So this only protects against reading from past the end of the file buffer, but not actually the data being the correct size. Hold on, read color chunk. How was this originally defined? Okay, so it also gives a maximum based on this. Okay, so I think that should allow us to load the materials correctly. There we go. Now we're also loading objects. And we've actually loaded completely successfully here. Or at least we've loaded without error. So we need to see how correct this mesh is. Okay, it's loading 1 mesh and 9 objects, which is incorrect. It should be loading 12 objects. So there's still some kind of error here. Yeah, it only loaded 1 object. Okay, so we go to the file again. We've read 680 bytes. And then the next thing, we've read the entire file. So again, something inside of here is reading incorrectly. Okay, so reading the vertices causes us to read the entire file. Okay, so at this point we have 699 bytes read, 701, that's fine. Then down here we have 14,000 bytes, or 147,000 bytes read. Actually, that's not the entire file. That's possibly the correct size. Yeah, I got confused there because it's both starts with 1.4, but that's possibly reading the size correctly. I don't know what the actual size of those vertices are. Ooh, but then it just skips to the very end without reading anything else. So something here still is reading the entire file. Yeah, we got another incorrect number for chunk length. And bytes read is 6. So the error must be inside of vertices. Okay, so here we read uint 16. That was correct on ours. Then the next one we read float. Okay, this reads a certain number of floats to the end of the file. So it's possible we're just reading like one too many floats past the end, and that's corrupting the file again. Okay, it might be that the data size is for a single float instead of a vector 3. I have nothing to back that up, but it's just a guess as to what would be going wrong here. That's still an incorrect number for current chunk length. Although we did read quite a bit less data, but that's to be expected. Okay, so the behavior in the original one is it just reads floating point data for the rest of the chunk. The P is a vector 3 object. It's an array of vector 3. The only actual data is XYZ, so P is an array whose size is the same number that's pulled out of this read uint 16. Yeah, I don't know what could be going wrong here. And I think this should be GLM vec3 as well. Okay, so the number of vertices or the number of floating point data that we should read is 3513. Each of those is 4 bytes long. That gives us 14,000 for the size, which is the same as what's right here. So I don't think that's the reason that this is failing. Okay, it looks like there's actually an error in read vertex indices. Okay, so here in the original one, it reads the number of triangles. And then for each num triangles, it reads one uint 16. Okay, so index count is 920. File pointer is at 14,000. And after reading that, it's at 16,000, which is kind of to be expected here. And we're looking at the raw index data. Why are there so many zeros in here? Okay, that might be part of the issue, is that I don't know what these zeros are referring to. Oh, okay, so when you read the index vertices, you read them in chunks of 4, but you only apply the first 3 of them, and then one of them is going to be 0. Uh, that's a very weird way to handle it, but we do need to handle this case. Okay, I see what the logic here is. In the original read index vertices, we have this for loop where you loop for num triangles iterations, and then for each num triangle, you read 4 vertices, and then you only save 3 of those. Okay, so this isn't the index count, it is in fact the triangle count, as the name implied. Okay, so yeah, that is kind of a strange way to handle this, and there's no way to do it with just a straight binary read like I've written here. Well, okay, we can iterate on triangle count. To Erwin Schrodinger in the chat, hello. If you're just joining, I'm in the middle of rewriting Linux Air Combat to run on Windows. And part of that means rewriting the model loading code to work with modern OpenGL instead of the old style, which is old school OpenGL. Okay, so for each triangle count, we need to read 4 vertices from the file. That means instead of reading triangle count here, we just need to read 4. And also we don't read it directly into the buffer. Instead, we need to create a temporary buffer. Okay, and that means that we need to then push 3 of these values into the index data for the object, which is really awkward because I did not include an API for that. What the heck? Okay, so the only way I've written it so far is that you can write directly to it. Oh wait, we do have a way to write directly to it, so that's fine. Okay, so this reads 4 uint16s from the file, and then only reads 3 of them, or it writes 3 of them into the object. Okay, looks like we're reading through the file correctly here. And it looks like it read through the entire file without error. Or at least without throwing an error. So let's see what the actual model looks like now. Oh, I need to move that to a lower line. Okay, we have 12 and 9. So it is actually loading the model correctly now. At least it's loading the correct number of models. The model viewer still shows nothing because I did not put any kind of 3D perspective here. So I don't know if that's correct. Okay, so one thing we can do is load this into RenderDoc and see how well the mesh is loaded. And we want to capture one frame. Let's see, we have bind vertex array, bind buffer for one buffer, and then another buffer. Okay, so I just realized we're only submitting 3 vertices to this batch, which means it's not going to render correctly because I'm only drawing 3 of them. So I need to actually change this to use the proper vertex count. See, this uses, okay. Oh, we're rendering something here. I can't really tell what that is. Possible we're not loading the data correctly. Okay, so this is something. Oh, that's the canopy of the plane. Okay. So yeah, we're only rendering one mesh out of all of them. And it did not actually look all that good either. Okay, so this is the orientation it was when it was rendering. These vertices do not look very correct. There's these weird edges going across them. But the general outline of the canopy is still visible here. You're watching the stream with a 20-minute delay. Your message wasn't weird. It was actually when I saw it in the chat, it helped me fix the bug, so it was still helpful. Okay, so we're rendering one mesh out of the 12 meshes that are on this model. So I guess the next step would be to load everything here. Okay, you know what? This bind call probably does not have the correct... Oh yeah, we're only rendering one mesh at a time. So we can actually just do this for multiple vertices, or multiple vertex data streams. Okay, the one mesh we have is the first mesh here. We need to do that for every mesh. Okay, now this should be able to render every mesh in the model. Here we go, that looks vaguely like a plane. So the index data here is getting messed up. That's causing the triangles to draw somewhat incorrectly. But we are rendering the plane at least a little bit right now. Hold on, I can launch this again in render doc. Okay, so we do have multiple color passes here. Or we have multiple draw calls in this color pass. Oh, you know what the problem is? I am rendering the vertex data directly, but the models are defined with index data, so I need to also change that. I need to find the index data for each model as well. Okay, yeah, so I'm binding the vertex arrays. I don't remember the exact way to do this. Yeah, something that's attached to the VAO is what stores the elements, which is what OpenGL calls the index buffer. Oh yeah, element array buffer for EBO. Okay, that should be fairly simple to add then. So inside this GL backend, all we need to do is create another buffer for the index elements. So also we need a way to store that buffer. Okay, now we have the mesh, so we can check the mesh has index data. And if it does, then we GL gen a new buffer. and we bind that to the GL elements buffer. I believe that's correct, the element array buffer. And then we can GL buffer data. And GL enum usage, which is just static draw. And I don't think we need anything else for that. Yeah, so just being part of the VAO means this is stored, or because it's located here, it's stored as part of the VAO. So with that in mind, we should be able to render this by calling GL draw elements instead of draw arrays. And then when we need to set the correct elements rendering mode, which is GL triangles. The count, which is the index data count. GL unsigned int. That's not the correct one I'm using right now, so I don't know what the... Okay, GL unsigned short. And I think this is optional, I don't need to set it. So if we do that, we should be able to draw the meshes correctly. There we go. Okay, so it was just an error with the index buffer. All right, so we are now drawing this mesh, or we're at least loading it correctly. We're basically drawing it in orthographic view, and there's no way to move the camera because I haven't written any camera code yet. But this means that we are loading the model properly. And it's recognizable now as an A6M2, which I believe is a 0. Yeah, so this is a 0 fighter plane, and it's recognizable as such. So the shader is just set to an orange color, and there's absolutely no other effects applied to it. But I think this is a good stopping point for what we have for the model loader that we've been working on for the past 4 sessions. If you want to join later on, I do this every Saturday for in the afternoons, at least central time zone. And thank you for joining. Yeah, and I'm not sure how to pronounce your name because it's in Cyrillic, but your comment about the J plus equals 3, that was helpful because that fixed a bug. So thank you for that. All right, that's the end of the stream today. Thanks for joining today. Bye.